Uh, thank you for the introduction, Jonathan. And it is really my pleasure and also actually an honor to be here to give this colloquium today. I'm a longtime APS user. I've been coming here since my graduate student days in the 1990s, and over the last almost 20 years, I spent numerous days and nights in Chicago, or sort of APS and guest house, and it feels like it's coming like to a second home. And then I actually counted the other day, and I've used actually 12 different beamlines at APS over the last 20 years. So that actually probably tells more about my sort of tendency to jump sort of around in different topics, so more sort of a short attention span of mine rather than actually my breadth of the interest. But today's topic that I'm going to tell you about, the quantum spin liquid, is not one of them. I think it is something that's fundamentally important and interesting to many physicists, and it's really at the heart of intellectual center of so-called the second quantum revolution. And for those of you who are not sort of familiar with that word, so there are sort of people sort of saying that the first quantum revolution was something that we all heard about, which is Heisenberg, Bohr, Schrödinger, and so on, developing quantum mechanics. But now, after all these years, we now understand something about quantum mechanics, and now is a time to actually sort of take or harness the so-called quantum weirdness of quantum mechanics and use it to do something useful and interesting, and sort of going towards quantum technology. And I believe the quantum spin liquid is a sort of intellectual sort of epicenter of this effort. So, so that's what I'm going to sort of try to convey, the excitement of this field to you today. And before I forget, I always wanted to thank the people who did a lot of work that's going on in our group, especially the stuff that I'm going to tell you today is done by Ken Plum and Jennifer Sears, but the other people in our group contributed tremendously. And of course, some of the work were done here at APS at the Sector 27 and Sector 9, and also some neutron scattering work done at the NIST. And we collaborate with sample growers around the world, and also I think the most important actually collaboration for me in this topic is being able to talk to many theoretical colleagues, especially people at Toronto, who actually sort of enlightened me about this very complex topic that I'm going to tell you today. Okay, so here's an outline of the talk. So I have two goals today, and it's always kind of difficult to prepare a colloquium talk to not just a physics audience, but very general audience. I'm assuming this is APS, so it's a very interdisciplinary institution, so therefore I'm trying to sort of simplify my message here. So the first thing that I want to tell you is, first of all, tell you what quantum spin liquids are, and so that's a sort of more introductory part, and it's a sort of a theory-heavy aspect. But also, I want to emphasize that the quantum spin liquid physics or quantum spin liquid research is not just something that it's in the imagination of a theorist, but it is real, and there are real materials that we can study. And that's the second part that I'm going to sort of emphasize, going over a few examples, especially focusing on sort of this so-called quantum spin liquid based on Kitaev's model. Okay. So that's the sort of two goals that I want to achieve today. But before doing that, I want to actually start by talking something completely different, which is almost my personal sort of a take on this quantum spin liquid research. So it's a sort of one perspective as an experimentalist. So to do that, I'm going to start with this view graph. So this is a figure that I have taken from Marvin Cohen's article in Physics Today about a decade ago. And this presents two models or two viewpoints of a solid. And on the left side, you have a sort of more traditional viewpoint of a solid, which is made up of an atoms forming a lattice with some electrons forming, say, block waves or something like that. And that's sort of what we usually think of a solid when we hear the word solid. But more and more physicists are thinking in the second manner, which is a solid is actually a sort of kind of an experimental system which you can actually probe by sort of gently exciting some elementary excitations and measure its response. And this is a sort of roundabout way of saying that solids are actually made up of many different types of quasi-particles, such as phonons or magnons or electrons. And of course, when I say electron, it's not just a bare electron, but it is a quasi-particle electron. It could be whole, it could be electron with a different mass, and so on. And over the years, we learned of condensed matter physics, learned that you can study properties of these quasi-particles using many different techniques, and especially useful is actually inelastic X-ray or inelastic neutron scattering, which can measure energy momentum dispersion relation. And so one example is if you measure energy momentum dispersion relation that looks like this linear line here, then you can immediately recall that the energy momentum relation of a photon looks like this, and that's because this photon is a massless particle. When a particle has a mass, its energy momentum relation, relativistically speaking, is changing to something like this, and then there is energy gap that is associated with the energy, the mass of this quasi-particle that we are interested in. So, so you can gain a lot of information about quasi-particles by doing scattering experiment. And pushing forward with this idea or this picture of a quasi-particle, I want to sort of contrast between metal and an insulator. And metal looks like this, and there are, of course, many more degrees of types of quasi-particles, but the sort of major ones are phonons and electrons and maybe magnons and magnetic material. And an insulator, if you actually think about it, everything else is pretty much the same, but the one lacking thing in an insulator is electronic degrees of freedom. And so it's not a stretch to actually say that metals are much more useful. And if you think about the applications we have over materials, then metals or semiconductors, I actually sort of putting this into a metal category, are much more useful. And the difference between these two are electrons. And the question that I want to pose to you is that what is it that makes electrons more interesting than other things? And you might say electronic quasi-particles have a charge. Maybe that's true, but what I'm trying to say here is that actually electrons are fermions while the rest are bosons. And that's important because electrons or fermions mean that they should obey Pauli exclusion principle, and that's crucial in understanding a lot of things, especially, for example, if you look at the periodic table, because electrons are fermions, and that's what the periodic tables are about. And also, the Fermi surface of a metal exists because of the fact that the electrons obey Pauli's exclusion principle. So that's basically what we are at. So as a sort of an experimentalist going forward and looking at this picture, you might wonder, okay, so insulators, which is actually more common than metals in the material world, can we actually have some kind of fermionic degree of freedom that acts like an electron in metal that we can use to do something useful? Okay, so that's actually something I sort of want to pose, and that is sort of in the sort of sense of materials research. I think that is kind of a driving force behind this interest in quantum spin liquid, because quantum spin liquid is an example which provides the ready-made fermionic degree of freedom to an insulator. And for example, in the well-known quantum spin liquids have a so-called spinon Fermi surface. So spinons there actually do a job of electrons in metals, and therefore you can actually use or harness, actually it's this fermionic degree of freedom for applications. And that's sort of something that I think is important for understanding quantum spin liquid. It is not something, trying to understand the exotic phase of some quantum magnet. It is actually sort of pushed towards trying to find a material which actually can have this low energy degree of freedom that's like giving you a Fermi surface-like property in an insulator. Okay, so with that, let's switch gear and then sort of talk about quantum spin liquid sort of introductory part about the quantum spin liquid. And a lot of people associate or sort of attribute the origin of quantum spin liquid to the idea of a resonating valence bond idea proposed by Phil Anderson in actually in 1987, but actually it sort of originated in 1973. 1973, that sounds like a very long time ago. Anyway, in this actually paper, which was written in response or sort of trying to explain the then newly discovered high temperature superconductor, Phil Anderson proposed this very interesting idea, and which actually contains the essence of what quantum spin liquid is. And actually, he used the word quantum spin liquid in this paper already. So what is it? So let's talk about resonating valence bond idea as a sort of a more poster child of quantum spin liquid in this initial part of this talk. So what is resonating valence bond state? And it actually goes back to the idea of Linus Pauling in 1930s when he was trying to understand the sort of geometry or physics or chemistry of a benzene molecule. So the structure of benzene molecule was known at the time, and it forms a hexagonal structure formed by 6 carbon atoms. And of course, Pauling is famous for his idea of chemical bonds, and he was trying to understand what kind of chemical bonds are present in this benzene molecule. So there's actually a hydrogen atom that I'm not drawing. So there's a bond to the hydrogen, and then 2 neighboring carbons take up 2 bonds. Then you actually have 1 bond left for this carbon atom. And a good student of quantum mechanics, Pauling actually thought about this, and then said that, so why don't, so there are 2 possibilities, right? So if you take a carbon here, then you can actually have a double bond on the right side or double bond on the left side. But quantum mechanics allows us to actually say that actually both are possible, and by this idea of a superposition. When you actually have a quantum mechanical system, then you can have this sort of linear combination of these 2 possibilities. And that's a superposition of these 2 sort of a state that gives you the final state. And that was termed a resonating state. A resonance between these 2 is another way of describing this. So Anderson comes in 1987, proposed that so the parent compound of cuprate superconductors are well-known insulating material called lanthanum copper oxide, which forms a square lattice of a spin half degree of freedom on each side. And it was well known that the parent compound of cuprate is well described by these spins on square lattice, which interact with the so-called Heisenberg interaction. And that's mathematically written in this way. And of course, this is really a 3-dimensional structure, so it actually forms a magnetic order, and that's all well established through neutron scattering and many other experimental techniques. But the intellectual or sort of conceptual question that the Phil Anderson asked at the time was that if we actually distill this into an essence of just a 2-dimensional system without any interaction between the layers and cool down to 0 temperature, and so then what is actual ground state of this material or this square lattice Heisenberg antiferromagnet for spin half? And of course, in the classical picture, we know that this is a nail order like this, shown here. And that also applies to S equal 1 or S equal 3 halves and so on. But at the time, it was not known what really is the ground state of this thing for S equal 1 half, which is the case for largest or strongest quantum fluctuation. So basically, Phil Anderson proposed that maybe actually it's not nail state at all. It is something called something like this. And this is sort of a kind of bad graphical representation of a resonating valence bond state. But what it is actually you take 2 spins, and 2 spins, if you can form a so-called spin singlet or spin triplet. And spin singlet state is non-magnetic, and something like this has the lower energy when you have antiferromagnetic interaction. So you can sort of imagine that there's a spin singlet on these two bonds and two bonds here and so on. So this is actually one way of sort of imagining the ground state of spin singlet, or sometimes often called valence bond state. Okay, so this is one example, but you can also think of, okay, so there's nothing unique about this one. What about this type of sort of coverage of a valence bond for a square lattice? Or what about this? And so on. And so there, basically, this resonating valence bond state idea comes in because you can actually say that yes, it's yes to everything, and it's the superposition of all these possible valence bond configuration that gives you so-called resonating valence bond state. And that's basically the idea of ground state for square lattice spin half antiferromagnet proposed by Anderson, which turned out to be wrong. It's actually nil state, that's the ground state. But that actually sort of stimulated a lot of interest and effort in understanding sort of or characterize quantum spin liquid in many different systems. So now that I gave you some flavor about what quantum spin liquid, an example, looks like, let me actually go on and then define what quantum spin liquid is. Okay, so there are actually no really good way of defining quantum spin liquid, and the best actually thing that we usually use is, so no magnetic order at any temperature. So if system doesn't order at any temperature, including t equals 0, then it's a spin liquid. Then that's really, so that's not really a definition, right? So and then usually there's all sorts of qualifiers following or caveats. So usually people disregard one dimension because one dimension system is trivially not ordered at t equals 0, so it's not really useful to talk about that. So let's actually just focus on 2 or 3 dimensions. And you have to exclude spin glasses or other frozen state because the frozen state is not really, so there is no dynamics important quantum dynamics is involved there. So that we are not really considering spin glass or other frozen state as a quantum spin liquid. And when I say the no magnetic order, it doesn't mean necessarily that no ferromagnetic or antiferromagnetic order. Even if you have a no magnetic order, apparent magnetic order, if the system breaks some kind of a translational or other symmetry, then that's also sort of not a part quantum spin liquid. And so continuing with the resonating valence bond example, you might say, oh, so this looks like a resonating valence bond, but what about this? And here, yes, it's perfectly okay to have the sort of a valence bond covering that looks like this, but immediately you can recognize that the symmetry between the vertical line and the horizontal line is broken. Therefore, this is not a candidate for a quantum spin liquid. Okay, so that's the definition that I can give you now. And then I know that if you're satisfied with this definition, that's fine, that's great, good for you. But probably you are not. Because it's like if your 5-year-old asks you a question, Daddy, what's a whale? And if you answer, it's not a fish. Right? It's perfectly correct. But that's really not the definition that your daughter will be satisfied with. Okay, so that's basically what this is. So by defining something with that describing what it's not is really not the best way. But so that's actually the problem. One of the problems that sort of intellectually we are facing in quantum spin liquid is there's really no good way of defining what is quantum spin liquid. There's this answer. But in the absence of any better actually explanation, this is what, as an experimentalist, find the most convincing. So no magnetic order at any temperature with some caveats. Okay, so still, that's not good enough. And then you can actually provide something more, and especially from a theoretical viewpoint. And that's, it has a topological order. So again, some people might think that that's actually not good enough because it's kind of like answering your, the whale question of your daughter by, a whale is a mammal that lives in a sea. So imagine telling that to your 5-year-old, right? So it doesn't really, I mean, it's true again, but that's probably not helpful in understanding this because you have to explain what mammal is and so on. So topological order, okay, this again, I have to explain what it is. So that's actually not a very good way. And then also it's actually, there's no one-to-one correspondence because there are some materials with the topological order, but that's not quantum spin liquid. But I think as far as I know, the quantum spin liquid should have topological order. And to make things a little bit worse, I'll sort of, this is the last slide with sort of these very complex jargons. Topological order, what's associated with the topological order is its excitation spectrum is necessarily described by so-called fractionalized excitations, such as spinons or anyons, and I'll come back to this. But going back to topological order, so to explain that, it is actually sort of not simple to actually what topological order means, but it is essentially, so for many of people have some vague idea what topology means. It's basically, baseball is different from donut, but coffee mug is the same as donut, right? So the idea is that if there's some shape, or so in both coffee mug and donut has a hole in it, but baseball doesn't. And so that's sort of a topological invariant quantity that is preserved, and that's the idea of topological order. And sort of pushing forward with this RBB example, I can give you some flavor of what that means. So if you take the RBB example and replace the oval with the line, it's just for the convenience of drawing, and you can have a RBB that covering that looks like this, or that, because it actually, I didn't say that it has to be neighbors, which is coupled or forming a singlet. And let's do a thought experiment. So let's take an RBB, one type of RBB covering configuration, and sort of draw a line and break bond along this line. Then you can count how many bonds are broken there. And there are 4 of them. And you can do the same thing for the next line and the next line, and you get this. So another configuration that I showed you before, and you can do the same thing, and then you can say that, okay, so this is 4, 0, and 4. And you can do another thing here, the same configuration I showed you previously, and then you can count these broken bonds, and this is. So then you sort of notice that there's something that's interesting is happening here, is that this is always an even number, okay? So the evenness of the number of broken bonds in this this exercise is one example of topologically invariant quantity, and that sort of tells you that there's something hidden behind this seemingly disordered state, but there's something that we can actually tell by. So that's basically topological order. What about the fractionalized excitation? So if you actually make an excitation in this topologically ordered phase, so one way of doing that is actually take one bond and then break it and then make it into a triplet. So you're basically going from singlet, S equals 0 to X equals 1, so therefore S equals 1 excitation is created. But what's interesting about this type of thing in this kind of valence bond, resonating valence bond state is that there is this free spin can actually form a valence bond with this spin over here and leave this spin free. Or this spin can form a valence bond with this one and leave this one free. And all these kind of reconfiguration doesn't cost any energy. And therefore, this free spin and this free spin, although created locally, can actually separate out far out without actually costing any energy. And that kind of process is described as a fractionalization because you are creating S equal 1, but you are split into these S equal 1 into 2 S equal half system or half excitations that's far removed from each other. Okay, so that's the topological order and fractional excitation flavor that I want to tell you a little bit about. But, and I want to talk about anyons a little bit, I want actually, because again, the anyons are some quasi-particle that's peculiar in only 2 dimensions. And so I don't want to sort of go into detail, but what I want to point out here is that the non-abelian type anyons are essential for so-called topological quantum computing. And for those of you who are familiar with some of this recent literature, probably heard or read about some so-called Majorana fermions. And that's as an example of an anyon that's useful for topological quantum computing. I won't go into more details because this is a very theoretically or conceptually sort of theory-oriented concept, although there are some experimental efforts. There's actually many good references, including there's a sort of popular article in the Scientific American on this topological quantum computing using anyons. So I'll stop there about this slide. And the reason is because it's getting into the realm where experimentalists basically lose interest, and I lose probably half of you already. So I'll stop here, and then sort of I want to switch gear and then talk about the experiment. Because if you actually look at this slide, then so there are 2 things that pops out to me. And one is magnetic order, no magnetic order. That's actually a simple concept. Whether or not there is or there isn't magnetic order is something that any experimentalist can test and then try to see. And then there's spinons. And for those of you who are familiar with neutron scattering literature, spinons are something that's actually quite well known in neutron scattering community and also in X-ray scattering recently, because we know how to measure spinons. And spinons can be measured both using inelastic neutron scattering as well as resonant inelastic X-ray scattering. And this work was done actually in the Swiss light source in this strontium copper oxide. And this one, neutron scattering work was done on the potassium copper fluoride. Unfortunately, both of these works were done on 1D spin chain. So one-dimensional material, which is actually ruled out in this quest for quantum spin liquid, we do know how to measure and study quantum spinon excitations. So experimentalists, this is actually quite a sort of familiar concept. So I want to actually take 2 of these things, no magnetic order and spinons, as a guidance for finding quantum spin liquid in real materials. Okay, so let's talk about no magnetic order first. And it's actually quite challenging. So if you think about it, this is actually from the textbook that I used for my 2nd year course. And here actually there's a sentence called that there's S equals 0 at T equals 0 is often called the third law of thermodynamics, which means that material or the things tend to order at 0 temperature. And of course, if you haven't heard about this, don't worry about this. It's not really a thermodynamic law like 1st or 2nd law, because there are many exceptions. However, there's a reason why it's called law, because in general, that's true. So in general, most of the systems will tend to order at T equals 0. So what can we do to actually prevent something to become ordered at low temperature? And that crucial ingredient is called geometric frustration. And so this is so nothing new idea, because it has been around for a long time, and even actually you can find the literature in 1950 by none other than Wannier calculating entropy of an Ising model on a triangular lattice, and then he concludes that the system is disordered at all temperatures and possesses no Curie point. There is no magnetic order. Okay, so. And that the idea is pretty simple. If we have a triangle where the interaction is all antiferromagnetic, which means that the spins want to point in opposite directions. So if we have up spin here and down spin here, then no matter what you put here, then you are not going to satisfy both of these the interactions. So that's sort of a simple idea of a geometric frustration that you can find in antiferromagnets. So that's great. So let's try to build a material that's based on these triangles. And the first thing that one can try is a triangular lattice. And it turns out that it's not that simple to find quantum spin liquid using this kind of things, because it turns out that most of the magnetic interactions are so-called Heisenberg interaction rather than Ising interaction. In other words, or actually, so the spins are spins can point in any directions rather than actually just up and down like in Ising spin. And if you allow that in triangular lattice, then you can actually find a unique ground state where these spins are sort of rotate by 120 degrees and forming this kind of lattice or three sort of sub-lattice magnetic ordering, so-called spiral order for Heisenberg antiferromagnet on a triangular lattice. So that's not a quantum spin liquid. Okay, so let's try something else. You can actually try to sort of rearrange these triangles. Instead of having one triangle forming, sort of meeting another triangle through this edge, you can actually have one triangle meeting another triangle through this corner. And that kind of a lattice is called a Kagome lattice because it's a sort of a pattern that's reproduced from the sort of traditional Japanese type of basket weaving technique. So that's one frustrated lattice, geometrically frustrated lattice that one can try. And there's another sort of direction, which is instead of staying in the 2 dimensions, you can actually think of a 3-dimensional geometric frustration. So the equivalent thing to a triangle in 3 dimensions is a tetrahedra. So you have this tetrahedra, which is again formed by triangles, but this actually have a natural geometric frustration. And you can form a sort of 3-dimensional lattice using this tetrahedra by sharing its corners. And that lattice structure is called a pyrochlore lattice, which is a very common, actually, crystal structure in many materials. And so on. So you can actually come up with some other lattice called the hyper-Kagome lattice, which is a 3-dimensional version of this one, and diamond lattice. And actually, your good old FCC lattice actually has some component of frustration. And there has been research going on in all these research sort of the lattices, and then trying to make a material that is sort of reflecting this type of lattice geometry to see if there's a quantum spin liquid. And in many of these cases, always there's some small perturbation that comes into play to ruin the whole thing and to make the system ordered or frozen and other things. So the only the sort of agreed upon, sort of probably there's a consensus about the quantum spin liquid is a Heisenberg model on a Kagome lattice. And first of all, this was actually not agreed upon among theorists, but by this large-scale numerical calculation done by Steve White's group, it is now sort of agreed upon that the ground state of Heisenberg model on a Kagome lattice is one type of quantum spin liquid. And about at the same time, there was actually heroic effort by Young Lee's group at MIT, who was at MIT at the time, who were able to grow a very high quality so mineral called Herbert Smithite, which actually has the requisite Kagome lattice structure where spin half degrees of freedom is lying on each sort of corner of the triangle. And what's important is that they were able to grow very large, actually very high quality single crystal with a very small defect, and then do inelastic neutron scattering to measure its magnetic excitation spectrum. And what they have measured is that, observed is that, as you can see here, these the hexagons are brilliant zone boundaries, and then there are these excitations that sort of spills over many brilliant zones, which is very broad and has some unique actually shape to it. So this is actually an example of a spin-on excitations that's found in 2 dimensions. And this sort of gives you that present one of the sort of better known example of quantum spin liquid in real materials. But this is sort of kind of one-off thing. This is an extremely difficult material to grow, and the disorders always comes into play, and very difficult to sort of replicate this success in many different materials. Okay, so what can we do? So I want to stop here about talking about geometric frustration as a sort of avenue to go into, and because it turns out that there is a different way to achieve quantum spin liquid, and that is proposed by Alexei Kitaev in 2006. Actually, the idea has been around for a long time, but he finally wrote up in 2006 and published there. So the idea of a Kitaev honeycomb model is this. So take a honeycomb lattice. Honeycomb lattice is not a geometrically frustrated lattice. There's nothing, it's a bipartite lattice. You can actually have a nail ordering in honeycomb lattice. But what's unique about this is Kitaev proposed that you have some Hamiltonian that looks like this, and which has sort of take advantage of the honeycomb lattice, where you have 3 bonds, and each of these 3 bonds have its own unique actually magnetic interaction, and that's actually the sort of the unique thing about Kitaev's honeycomb model. And so I'll come back to this a little bit more later, but not only did he propose this model, but he solved it, and he showed that you can solve it exactly, which is extremely rare in physics models. And more importantly, actually, he found that there are a bunch of different quantum spin liquid phases that's found in this model. And one of the important things here is that depending on actually the strength of this x, y, z direction interaction, you can actually have a gapped spin liquid or something so-called a gapless spin liquid. And among the gapless spin liquid, so the low energy degree of freedom in this case is Majorana fermion. But what's really important here is that in this particular phase of gapless spin liquid, if you apply magnetic field here, you will find non-abelian anyons. Again, so if you pay any attention to the slide that I asked you to forget about this small box about anyons, the one thing that I sort of want to recall or sort of ask, actually, I don't want to go into, is that it's a non-abelian anyons that is essential for topological quantum computing. That actually was, again, proposed by Kitaev. So Kitaev proposed a way of doing topological quantum computing, and he came up with a model that explicitly shows that how it can be done. So that's actually quite remarkable, and then so that's why he's one of the, I guess, the sort of pioneers in this field. So anyway, so that's great. So that's all good and interesting, maybe. So let's look at the Kitaev's model more carefully. So what this Kitaev's model requires is that there you have a spin half degree of freedom and it is each side, but they have 3 neighbors, and the interaction with each neighbor is all different. Essentially that. So you have 3 neighbors all telling you to do different things. So natural thing is that you are frustrated. So at each site, there is a natural frustration associated with the fact that you have 3 sort of different bond-dependent interaction. That sounds like a really unlikely thing to find in real life or real nature, right? So I don't think Kitaev actually predicted or envisioned that this will be materialized in real system, but it was George Jackelli and Ginia Kalulin who actually were studying material with a large spin orbit coupling and quickly realized that you can actually realize this type of Kitaev interaction in real materials. And I'll go into a little bit of detail on this one. So material like iridium, so if you put iridium in oxygen octahedral environment, and there's first the crystal field splitting because of this cubic crystal field is so large that you're actually essentially removing the EG electron systems, and then you're left with basically 3-level T2G system with the 5 electrons. And starting with that, if your next highest energy scale is spin orbit coupling, then the end result is that you are left with this singly occupied effective J equal 1/2 state and effective J equal 3/2 state, which is all field. And this effective J equal 1/2 state is sort of strongly spin and orbital sort of entangled state, because it's not just a spin over spin down. It is, the wave function looks like this with 3 orbitals all mixed in with the 2 spins. Okay, so that's the peculiar thing about the material with a strong spin orbit coupling. So if this is not strong enough, then you are not going to achieve this. But what's more interesting is if we actually put these two things together and investigate its magnetic interaction between these two effective J equal half moment, then you realize that the dominant contribution that you initially think about is actually this super exchange interaction through the intervening oxygen that's lying over here. And then you basically think about hopping from here to here and hopping from here to there. And the important thing is there are two paths. And it turns out that because of the, in this that type of strong spin orbit coupled system, these two paths interfere destructively and basically cancel each other. And that means that you have to go to the next highest level of a perturbation theory. And they found that if you do that, then it actually gives you Kitaev interaction. And the reason is because this has a strong spin orbit coupling with the 3 orbital states mixed in. Okay, so that's great. So they provided the direction. So if you take a strong spin orbit coupled material, which has this edge-sharing octahedral sort of magnetic pathways, then you might be able to realize a Kitaev's quantum spin liquid. And immediately actually following that prediction, there's a material, sodium iridium oxide, which was synthesized by many groups actually, but Yogesh Singh and Philip Gegenwart published first in this thing, and they were able to grow actually a fairly large single crystal of sodium iridium oxide. And you can see that the structure of this is exactly what you expected. So first of all, it's a honeycomb lattice. And honeycomb lattice is formed by octahedra of iridium and oxygen, but this octahedra is connected through this edge-sharing network. So this is almost exactly what you expected from Ginyat Kalulin and George Kelly's proposal. So, okay, great. Is it a quantum spin liquid? And sadly, the answer is no, because it orders. So immediately after synthesizing this, they were measuring this magnetic susceptibility, and then they saw that there's a magnetic ordering happening around about 15 Kelvin. And soon afterwards, John Hill's group at Brookhaven did a resonant X-ray scattering work done on this material, showing that actually the magnetic structure looks like this, and so-called zigzag antiferromagnetic ordering, where the spins along this honeycomb zigzag is all ferromagnetically ordered, and they are coupled antiferromagnetically between them. Okay, so that's unfortunate. So is that the end of the story? And it turns out, no, people are now going beyond that effort and then trying to synthesize many different analogous structures. So one example is hyper honeycomb lattice called beta lithium iridium oxide. Beta phase of lithium iridium oxide, where it's essentially honeycomb lattice, but it's convoluted three-dimensional way. And there's another gamma phase of lithium iridium oxide synthesized by James Analytics group at Berkeley, which is, you can see that there's a honeycomb lattice, so the next honeycomb is twisted, and so on. So that's actually kind of like honeycomb lattice, but slightly different. But in both cases, magnetically ordering sets in, so therefore they are not quantum spin liquid. But what's interesting direction that's proposed in this work done by Hide Takagi's group is that if we actually put this material in pressure cell and pressurize this using hydrostatic pressure, then magnetic signal drops significantly around 2 gigapascal. And this is actually XMCD work done at APS. And that actually is a strong signature or indication that magnetic order might be suppressed in high pressure phase, and maybe there you have a quantum spin liquid. And that's still, jury is open, but that tells you one direction. So even if you have a magnetic order system, you can perturb this to achieve a non-magnetic or a quantum spin liquid phase. Okay, so with this backdrop in the backdrop, so we were thinking about our next move when we were studying this sodium iridium oxide. Instead of trying to come up with a different structure, let's stay with the honeycomb lattice structure, but let's actually think about switching the main metal ion. So instead of iridium, what if we use ruthenium? Ruthenium actually can have a ruthenium 3+, which is 5D electron systems. But of course, the worry is that we need a large spin-orbit coupling, and to get the way to get large spin-orbit coupling is going down in the periodic table rather than going up in the periodic table. So what can we do about this one? So it turns out that what's important in talking about energy scale is not necessarily the bare strength of the energy itself. It is always when you compare energy, one energy to another energy, right? So you cannot say spin-orbit coupling is too small or too large unless you can compare it to something else. So what is it that we want to compare it to? And it turns out that it is the small additional crystal field splitting due to non-ideal geometry of octahedra. So when I showed you this diagram, I assumed that you have a completely octahedral sort of environment. But if you actually look at the crystal structure of sodium iridium oxide, then it actually has a sort of squished from top and bottom. Therefore, the angle between these things is larger than 90 degrees, 95 degrees, and angle in sort of sideways is slightly smaller than 90 degrees. And that actually gives you additional splitting in the energy levels that splits these two levels. And you can actually study that using RICS. And in the work done here at the APS, we were able to actually measure the splitting between these two energy levels and show that that is much smaller than the whole energy scale. But that also gave us an idea that the way to actually make the ruthenium or other materials with a smaller spin-orbit coupling work is to find a material which has an ideal cubic or sort of octahedral geometry. And that's when we stumbled upon alpha ruthenium chloride. And if you actually look at the structure, it looks almost like this iridate material that I showed you of a honeycomb lattice structure. But if you look at the actually individual octahedra, all the angles are very, very close to 90 degrees compared to the iridate I told you about. So that means that this will be, so the non-octahedral crystal field splitting will be very, very small. And therefore, we have a chance to make the spin-orbit coupling relevant, even in the case of a ruthenium-based material. So, and this material was actually not new. It's known for a while, actually. So I asked my talented graduate student, Ken Plum, to synthesize this, and we did X-ray absorption experiment. And indeed, when we compare this L2 and L3 edge absorption spectrum, we can sort of show that the spin-orbit coupling is relevant in this material, and therefore, Kitaya physics must be really important in this thing. Sadly, again, it's a sort of a kind of a recurring theme that it still orders magnetically. So this was work done by another grad student, Jennifer Sears. So when we measured the magnetic susceptibility, it shows clear magnetic order of a single crystal sample. And we can actually do neutron scattering because ruthenium doesn't have a problem with the iridium in terms of doing neutron scattering. So we actually did neutron scattering work on this material. And unfortunately, these crystals are all very small, so we actually had to make up a lot of array of these crystals to actually do this kind of the neutron scattering work. But in the end, we showed that there is the magnetic order in this system. Ordering temperature is about 7 Kelvin. And the ordering is, again, zigzag ordering. That's the same as sodium iridium oxide. But the interesting thing about this one is it's not the end of the story, because when you actually apply magnetic field, something interesting happens. So this magnetic ordering that I showed you here, so this peak, looks very small, but that peak actually decreases and then goes away when you apply magnetic field of about 8 Tesla. And that's an incredibly small magnetic field scale, actually. And you can actually sort of plot the phase diagram of temperature and magnetic field, and you actually can see that magnetic order is suppressed to 8 Tesla, this is the 8 Tesla thing. And above this magnetic field, if you continue to increase your magnetic field, you are creating an energy gap in the system. So you can sort of probe the energy gap by doing specific heat measurements, because if there's a specific energy gap, then there is exponential suppression of magnetic specific heat at low temperature. So here's a sort of 9 Tesla, 10 Tesla, and 11 Tesla. As you increase the magnetic field, the gap size increases. So you can actually plot the magnetic energy gap as a function of a magnetic field on this side, and then you can see that this one actually goes down to almost to 0, around somewhere around the 6 to 8 Tesla. It's not clear why they actually do not match exactly over here, but clearly it's sort of it's reminiscent of a sort of a very textbook-like quantum phase transition, phase diagram, and some interesting sort of quantum fluctuation plays a role in suppressing magnetic order here and then creating this gapped quantum paramagnet phase in this ruthenium chloride. You might have noticed that this is really exciting, and if you remember the original Kitaev slide that I showed you, the really interesting phase in Kitaev model is when you have a magnetic field in the isotropic limit, when you have non-abelian anyons that you can use for topological quantum computing. So then, is it really it? Is it there's a gapped phase that you introduce by applying magnetic field in Kitaev model? And unfortunately, actually, that's not the case because for that to materialize, you actually want to apply magnetic field along the direction which is perpendicular to the honeycomb plane. But in this case, we are applying magnetic field in the honeycomb plane. So this is not exactly that's what's happening. And it's not clear at the moment what's exactly happening here because this is extremely rapidly developing field. I don't know about you, but I have never seen this. I'm working on one project, and then within 6 months, there are like, I don't know, 10 papers popping up in exactly the same thing. So it's a sort of the situation here is a little bit murky, and then so I think as we go along, we'll have a little bit better understanding of exactly what's happening in this phase diagram around this thing. And yet, sort of, so to put new wrinkle in this thing, there is a recent actually preprint archive paper saying that if we actually apply hydrostatic pressure, you are inducing yet another quantum spin liquid phase in this ruthenium chloride. Last but not least, I've been talking a lot about the way to suppress magnetic order. I've been obsessed about magnetic order suppression and so on. But the other sort of experimental sort of knob or tool that I sort of told you as a guide in this adventure is magnetic excitation. It turns out that probing magnetic excitation in this Kitaev type of material is very difficult because, first of all, a lot of them are iridates, and iridates are very notoriously difficult for studying with neutron scattering. And of course, there's great risks that we can do here at the X sector 27, but energy resolution is not there yet. So energy resolution, I know that there is a high resolution effort going on in this sector 27, but it's still not there to actually address the what's the sort of the spin-on excitation spectrum in iridates. Ruthenium chloride is great for another reason because actually ruthenium is neutron friendly. You can do neutron scattering as long as you have a large single crystal. And unfortunately, that's not what we had, but these guys at Oak Ridge were able to go large single crystal of ruthenium chloride, and they were able to do inelastic neutron scattering work on that. And there was actually, again, this is a really competitive field. Another group in Korea actually did a sort of a similar type of inelastic neutron scattering work on the ruthenium chloride, and they essentially show similar magnetic excitation spectrum. At low energy, you have this kind of star-like sort of excitation in reciprocal space. So this is inelastic neutron scattering intensity as a function of momentum in momentum space in 2 dimensions. So in this low energy sector, you have this star-like thing that's sort of merging into sort of more circular behavior up here. And if you increase the temperature, it's still there. So even if the magnetic order is gone, this excitation is closely related to the spin fluctuation that is inherent in this spin Hamiltonian of this system. And you can actually compare your result with a theoretical calculation that assumes that Kitaev interaction is quite sizable in this thing, or sort of when you have a Kitaev type of ground state, then maybe it's similar. So there's a sort of faint sort of a lobe that's pointing in all these 6 directions. Maybe it's similar, maybe not. So again, this is some very rapidly developing field, and I'll probably have a more story to tell you in few years, actually. Okay, so that's about it in terms of this thing. So quantum spin liquid, again, so I want to emphasize the sort of main sort of thing that I want to tell you is that quantum spin liquid is not just a sort of exotic quantum magnetic model. It is something that we are sort of trying to achieve because it will provide us with the fermionic or spin-on-like degree of freedom in insulating material so that we can actually use it to do something useful. And one avenue that's proposed is topological quantum computing, but who knows what might come about. I mean, if once you have a spin-on Fermi surface, it could be really useful for many applications, including thermal transport and so on. So reiterating what I said, quantum spin liquid in theory means that there is no broken symmetry, but which has topological order and fractionalized excitations. But in real sort of experimental situation, what I'm emphasizing here is that you need to find a material which doesn't have magnetic order, and you can achieve that by through geometric frustration or sort of inherent interaction frustration through Kitaev interaction. And there is one known candidate for quantum spin liquid, which is Hubbard-Smithite. And for Kitaev quantum spin liquid, there are actually a number of candidates, such as a beta lithium 2 iridium oxide or ruthenium chloride under in-plane magnetic field or pressure. And all these things are actually open question that is actively investigated in these days. So again, so I think understanding these things will really help us sort of formulate better understanding of quantum spin liquid. And another thing I want to sort of mention here is that the quantum spin liquid is not just one thing. It is a class of material which has basically a spin-on or anionic Fermi surface or some, anionic Fermi surface doesn't really make sense, but anionic degrees of freedom at low energy, and that can be a whole slew of things. And we are really starting point where we can sort of see one spin liquid here, one spin liquid there, and then we'll probably, in the end, end up with a sort of classification of different types of quantum spin liquid that we can sort of study using many different experimental techniques. Okay, with that, let me stop here. Thank you.
Yeah, it looks like the HH on the theory is very different from that on the experiment. Is that something to be worried about?
Yeah, so I mean, this is arbitrary scaling by my PowerPoint mouse. So I sort of scaled it to roughly match this, so to compare. So it's not just sort of direct. So if you look at this paper, they have a sort of a side-by-side comparison, which looks a little bit more convincing. But again, you have to take a sort of comparison between theory and experiment in an experimental paper with some grain of salt, because you know that this theoretical calculation was done knowing what the experimental result looks like. So anyway.
No more questions? Well, let's thank
So I was very clear, right? I was very clear.
Let's thank Professor Kim again.
Thank you.